Good morning. Okay, welcome. Welcome to the end of this summer course on research methods. So this is lecture 21, and tomorrow we'll have lecture 22, and that's it. Um so I hope you have learned something, right, from these 6 very intense weeks on research methods. Well, right. So that's what this class is about. So previously, right, we talked about inferential statistics. That is, how do we make statistical inferences? We said that typically we want to know something about the population, right? And we want to know, for example, what's the average opinion, right? The mean uh, opinion that is indicated by all the individuals in this population. But of course, we cannot do that. Therefore, we can only know about this population by drawing a sample. Right? Whoops, this sample is too large. By drawing a sample from this population, and from this sample, which contains smaller number of data points, right? We can calculate, for example, the mean of this sample more easily than we can with the population mean. So, for example, we'll calculate the mean to be 3.8. Okay. Um, we know that this will provide a point estimate, right, for the population mean. But we also know that because this is only one random sample from the population, if we draw different samples, a second sample, a third sample, right? uh, we are going to have different sample means. So, for example, this will be a little bit off. Well, maybe a little bit off, right? From this sample, 3 point, I don't know, 9. This will be 3.5. Okay, so that means each time we draw a different sample from the population, from the same population, we will have uncertainty, right? Uncertainty about which mean is exactly the population mean, right? Or is more closer to the population mean. Well, from a statistical perspective, if these three samples are all representative, right, of this population, then any one of the three means are possible. So therefore, in addition to have a single point estimate, 3.8, 3.9, 3.5, doesn't matter, right? As long as we have one point estimate, it's often very useful to also have an interval estimate, right? To have a lower bound and to have upper bound, so that we know the extent to which, right, the point estimate of the population mean will fluctuate. So let's say, and we know through the previous lectures, right, how to calculate or how to construct this confidence interval, right? It is called confidence interval because the exact boundary values that will be able to generate depends on the confidence level we want to be at, right? If we want to be very, very confident, say 99% confident, right, that the sample mean that we obtained will include the population mean, this confidence interval will be very wide, right? A wide interval includes more values, right? And that will give us more confidence in including the population mean. But of course, a wider interval also means we might actually include values that are not really good estimates of population mean, right? So in that case, we want narrower confidence intervals, like 80% confidence interval, for example. Uh, in this case, we trade off confidence for precision, right? If a value falls in this very narrow confidence, then we shall be very comfortable in saying, well, then we do have pretty good evidence, right, that our estimates is close to the population mean. Okay, so this is one way to understand this intervals. Then of course, typically we use 95%, right? This is the um, usual confidence level we'll be at. And it turns out, at least for normal distributions, right, for different confidence levels, we have different z values. We have z for 0.99, we have z for 0.95, right, and we have z for 0.80. So if 0.95 is the most commonly used, or 95% is the most commonly used confidence level, then it will be a good idea, right, to memorize the value of the associated z, right, these two. Okay, so this is given. Then we know how to construct this interval for based on the point estimate, right? We know that ci, right, 95 equals to the point estimate here. It will be the mean, right? That's our point estimate, plus or minus, right? We need boundary value. So this will give us the upper boundary value, the lower bound, and the z value, right, associated with the confidence level 0.95, and then the standard deviation of mean, right? Because standard deviation, SD, right, describes the dispersion, right, of the sample value. But it's a very special type of SDs. We call it standard error, right? So it's SD divided by the square root of sample size. So that will give us the 95, or confidence level at any confidence interval at any level. Okay. And similarly, we also talked about how to construct confidence 95 confidence interval for proportions. Proportions. Say point or 56% of individuals support legalizing marijuana use, right? So that would be a point estimate of the proportion. And again, we need boundary values, so plus minus. And again, we have z, right? So it will be z 0.95, or the z value for the 95% confidence level. Again, we need standard deviation, the standard error of this point estimate, right? So it turns out it is, we have the same denominator, but the numerator is p times 1 minus p. Okay? So that again will also give us an idea of how the extent to which, or the degree of fluctuation for this point estimate of population proportion, right? We also know that based on the calculated intervals, right, for proportion or for mean, depending on whether this interval includes a certain reference value, right, we can make some statistical inferences. For example, a critical reference value for proportions is 90 is 50%, right? 50%, because 50% really is the cutoff value for between a majority and minority, right? So if you have a proportion that's greater than 50%, that means you have a majority. And similarly, for sample mean, right? So especially when we're talking about attitudes, right? We'll typically use the sort of neutral point, right, as the reference value. Say on a 7-point scale, the neutral point will be 4, representing neither disagree or agree. Okay, so an important conclusion that we can draw from constructing these interval is to say, well, whether or not, right, the population people from the population, right? Not just from the sample. Because from this sample, you would say, well, because the sample has a sample proportion that's greater than 50%, then that means the majority of the respondents were in favor of this particular issue. But that may be true for the sample, but it might not be true for the population, because we know, right, there will be fluctuations. So we do want to know to what extent this 56% will fluctuate, right? So that's where the CI will be very useful. So if this 95% confidence interval, right, does not include 50%, right? So let's say that the lower bound is 51 and the upper bound is 59, right? So that's good news. That says, despite fluctuation, despite this fluctuation from 0.51 to 0.59, right, for the population proportion, we still have a, not a huge but clear majority here, right? That's because the lowest possible value at the 95% level is still greater than the cutoff or the reference value. So that means the majority of the population is likely to be supportive of this particular issue, right? And similarly, right, depending on whether this interval includes this neutral point, let's say 4, right, it could be 4.5 and 5.2, right? So if this is the case again, right, despite the fluctuation, despite that, the population average population opinion might be as low as 4.5, still, right, it's greater than or higher than the neutral point. That means they do have an attitude that's in favor of the issue, right? In contrast, right, if the confidence intervals include these reference values, right? For example, it's not 51, but 0.45 to 0.59. That means yes, a single estimate could be as high as 50.56, but if we take into consideration of the fluctuation, right, the uncertainty that's associated with this point estimate, the support rate could be as low as 0.45, which is lower than the cutoff value for majority minority, right? So that means we can conclude or claim that this population has majority opinion on anything, okay? Because at this end it will be clearly a minority, but at this end it will be clearly a majority. So, and because either of these values or any of these values on this continuum is possible, right? So there's no way for us to conclude that there's either a majority or minority, right? Both are possible. Same right here. If we don't have a 4.5 as the lower bound, instead we have 3.5 as the lower bound. That means this interval includes 4, the neutral point. So we could actually so if a population actually have this as its average opinion, right? That means actually the population as a whole is against of this issue. But if it turns out it is equally possible, right? Given that all these values possible estimates for the population, their average opinion could be as high as 5.2, which will be in favor of the issue. So again, if any of these values from this interval are possible, then again we cannot conclude whether this population is in favor of or in opposition to this issue. Simply we don't know. Okay, we need more information. Okay. All right. So again, that's a sort of repetition for the previous 2 or 3 classes. I repeat it here again, or repeat them here again, because those are pretty important and content that may not be very intuitive at the first exposure. Okay, I hope you find it intuitive, but chances are they're not as intuitive as other classes you might take from this department. So, and I do believe that repeat exposure is perhaps the only way that you can make certain content to sink in, so to speak, right? So I hope, right, by repeating these information with these examples, right, And with these explanations, you will sooner or later have a moment of light bulbs, right? That will be great. Okay, good. Enough for the recap. Okay, so today and tomorrow we'll be talking about two very simple, well, seemingly simple, but actually very foundational and very important statistical tests, right? So far, what we've been doing is actually we have been talking about statistical tests, right? We're drawing statistical conclusions. But so far, we have been playing with a single value, right? That is what we can do, what kind of conclusion we can draw from a single value, right? Or single value from a sample. But from today, well, I want to say from today to tomorrow, but within these 2 days, we are going to look at what we can do with two values, right? That is from one sample, instead of measuring only one property, what if we measure two properties, right? Two means. What can we do with these two means, right? What kind of information we can gain from them, right? So that's why we're going to talk about bivariate relationships, right? Bivariate. So bi, as we said before, means two. Variate means there are two. Variate means actually variables, right? So that means what will happen if we have two variables? What can we do, right? What kind of conclusion can we draw by measuring two instead of one mean, right? Or mean of different properties. Okay, let's look at an example. So correlation. Correlation is just a word for statistical association, right? Um, and establishing statistical association, some will say that this is the only task for social scientists. And they say that it's a little bit exaggerating, but I don't think they're fundamentally wrong. They're right because correlation or statistical association between two variables are at the very, very fundamental level, the most important topic in any statistics. Well, 99% of statistics. Well, um, at least for social scientists. But, establishing statistical associations is not the only, well, it's not only just an academic game, right? It's actually very relevant to all aspects of our life. So, for example, teachers and parents, obviously, and you, I hope, are very concerned with this question that is, what is associated with good or bad academic performance? That is, if we want our academic performance to be better, what will typically go with that? Well, you would say perhaps, more studying time or diligence, right? Perhaps will go with academic performance or concentration or uh, um, economic resources, right? If you are from a relatively well-off family, then chances are you might have the ability or opportunity to receive better education, then you might perform better. So, right, that's an important question, right? For business people, right, or your boss, your future boss at any kind of firm, right, or company, they will be concerned with what will go with business growth, right? They want to sell more stuff, but then they want to know, right, um, what is going up, right, with the sales number is because of the age of people, right? Are people going to buy more of our products as they age, or is it because of I don't know, their family background, their ethnic background, well, any kind of features, right, about their customers. So if they can figure out, right, what is going up or down with their sales number, they can do something about it, right? They can make their commercials perhaps more targeted, right? More customer targeted, so that to further boost their um, their wealth. Okay. Doctors, physicians, they are certainly very concerned about what goes with health, right? What goes with longer or shorter lifespan, right? Eating more vegetables, presumably, right? What goes with a healthier body. Cigarettes or substance abuse will probably go with lower health overall. Okay. Uh, Politicians are no exception, right? I believe the single most important question that Donald Trump and Hillary Clinton are both very concerned with in their mind is how can I get more voters, right, to vote for them, right? And I believe their campaign managers working very hard to figure this question out, right? So is it because for example, are what kind of population more likely to vote for Republicans, or what they can do so that they can get more votes, right? Or what can they do so that their opponents will get less vote. Okay, so again, invariably in these examples, we have first of all one core variable, target variable here, right? That is academic performance, business growth, health, voting decision. These are all variables, right? Because they can certainly take on different values, right? Higher or low growth, poor or better health, voting for this or that party, higher or lower GPA, right? And then they usually invariably would like to find out what is another variable that would go with their target variable, right? It's because of I don't know. Uh, okay, economic issues, right? Um, if they have certain kind of policy about taxation, right? Would that increase their votes, or as we say, substance abuse, right? Drinking more or less, that will impact health, or um, age of the customers, right? Would that be associated with the profit of the company, or studying time, right? Time spent studying, is that gonna related to how good or bad a student perform in school? So invariably, people from all aspects of all kinds of professions are trying to establish correlations, right? So that's why this is a very, very important topic. And of course, there are more examples. Okay, so let's understand then, how do we calculate this correlation by hand, right? By working through a very simple and example, so that we have better understanding about this very important topic. Okay, so imagine that Andrew, or anybody, right, surveyed a sample of UHN students, and he is very interested in whether or not, right, students' political ideology, from very liberal to very conservative, correlates with their support to gun control, ranging from strong opposition to strong support. Okay, and this is, let's say, part of Andrew's data. Okay, so or all of his data. Okay, so because of budget and time, he only surveyed 5 people, which, by the way, will be too low, right, for any sound analysis. But this is an example, right? Let's say he surveyed 5 people, so respondent 1, respondent 2, all the way to respondent 5. And for each respondent, Andrew asked 2 questions. The first question is, what is your political ideology, right? So this guy circled 1. Andrew also asked his, all the participants, what your attitude toward gun control will be, and this person scored 2, right, on this question. So the second respondent scored 2 on the first question and scored 4 on the second question, all the way down to the fifth respondent who scored 3 on the first question and 2 on the second question. Okay, so this is the structure of the data. Okay, very easy to understand, right? Well, respondents, we have one variable which takes these values, and we have a second variable that takes these values. Okay, I hope that makes sense. Okay, so what we can do now for Andrew, or what Andrew can do, is to figure out, is really the case that um, people's attitudes toward gun control depends on their political ideology. Okay, so typically, right, as you know, my understanding of of this very touchy issue in this country is that liberals tend to have um, more sort of support toward gun control, where conservatives, they're saying, well, we should really respect our the ideas of our founding fathers, and everybody should you know um, possess a gun. Okay, I hope I did not make mistakes here. Anyway, so that suggests a sort of association between political ideology and gun control. But is that the case, right? Is Andrew's suspicion correct? To confirm that, right, we need a technique that's called the Pearson product moment correlation. This is a horrible name, but it's that should not concern us, because Pearson is the person, Carl Pearson, is the person statistician who invented this technique, and it's called product moment because oh well, that's sort of the mathematical methods they use to derive the correlation, which should not be our will not bother with. Okay. Anyway, so just remember this is our technique method, and technically, sort of most stringently, right, strictly speaking, Pearson product moment correlation can only assess the association between two continuous variables, meaning variables measured with interval or ratio scales, right? Interval scales like attitudinal continuums, right? Ratio scales and interval scale with a true 0 point, right? Anyway, just remember, right? So these, well, the Pearson product moment correlation can only be computed for continuous variables. Then you might ask, well, what if I have categorical variables? For example, I assess people's gender, right? So man versus woman, and assess whether they vote for, so with man, with woman, and assess their sort of party affiliation. Okay, so we have Republican with Democrats. So obviously then we don't have continuous variables here, right? This gender obviously is a categorical variable. Party affiliation is another categorical variables. Then what do, right? So this will be our topic for tomorrow, right? How to calculate association between or correlation between two categorical variables. So today we'll be focusing on the correlation between two continuous variables. Okay? All right, so because we measure people's attitudes, and we typically treat attitudes as continuous variables, so that means we can use Pearson product moment correlations. And we've seen this before, right? So Pearson product moment correlation typically is denoted by this lowercase r, right? And we call it the coefficient for the correlation, right? It's sort of it's a point estimate. So again, right, we imagine Andrew does not just only want to study the 5 people that he surveyed. He want to study the entire population of UHM students, but of course, right, he can only study a sample from it, and this correlation is based on a sample. So essentially, Andrew is trying to establish or calculate a sample correlation, which will be a point estimate for the population correlation, right? For the correlation that's that's actually to be estimated from the population. Okay, so coefficient essentially will be in point estimate of the population correlation. Okay, see, everything connects. Okay, so certain properties for this coefficient, right? It has a boundary from -1 to 1, so that's a very nice property, right? And to understand these numbers, right, first of all, we need to understand the sign is very important. The sign denotes or determines the direction of association. So if we still remember, right, from way early on, perhaps the first week, we talk about the direction of correlations, right? We said that, for example, um, time spent studying, we have GPA, right? So we typically think if you spend more time studying, you'll have higher GPA. That's a positive correlation because the values of these two variables, they go in the same directions. As you spend more time studying, you have higher GPA. Boom, right? Moving in the same direction. So that's a positive correlation, right? So a positive sign means a positive correlation. But for whatever reason, right, it's also possible that the more time you the more time you spend studying, the more tired you get, and you become very irritable and tired of studying, and therefore you have lower GPA. Okay, well, I hope that's not the case. Anyway, so that you will have a negative correlation. That means as the value of one variable increases, you have the value of the other variable decreasing. So when the values of the two variables are not moving the same direction, right? This one is increasing, this one is decreasing. We say that these two variables have a negative correlation. Okay, so a negative sign determines the that this correlation is negative. Okay, all right. So that's about a sign, and the numerical value, right? 1 here, or later on we can see some other fractional numbers. Uh, it, it sort of assesses or estimates the strength of the association, how strongly these two variables are related. Or in some cases, two variables can be very, very strongly related. That's, um, for example, well, I don't have a good example here. Or, I do have a good example here. That's, weather and amount of sweat. How about that? If it gets warmer, you sweat more. I think that's a pretty good positive association, right? And you are very certain that this is gonna happen, right? So for any healthy individual, right? If the weather is warmer, you are going to have more sweat than when the weather is cooler. Okay, so when you are very certain that this is gonna happen, or you think there's a high probability that's gonna happen, that means these two variables have strong association. In contrast, and that's going to be denoted by a larger number that's very close to 1 or -1. Okay. um, in contrast, we can have weak associations, for example weather and, let's say, GPA. Well, weather might impact GPA, right? Perhaps when it's very cold, you have nowhere to go, so you are stuck in home, and then you have nothing better to do than to open a book and study. Good job. You improve your GPA, right? But it's also possible that because it's so cold, you'll rather just stay home and wrap yourself with a blanket and start to daydream. Therefore, you don't have good GPAs. So that means in this case, the the possibility that GPA, right, will increase with weather is not a certainty, right? It might happen, it might not happen. We don't know, right? So there might be some association, but even if there is, it's gonna be very weak, right? So that's what I mean by the strength of association. So this is it's probably gonna happen, but we don't know, right? Very unlikely, probable. Okay, so that's the meaning of strength of association. Okay, what I'm doing here. What I am doing here. Okay. So yeah, larger values indicating that the correlation association is stronger. Okay, let me ask you then to see if you truly understand the meaning. Okay, so now imagine we have two correlations. One correlation is negative 0.8, the other is positive 0.6. Let me ask you, which is a stronger correlation? Which is a stronger correlation? So you should pause here before I announce the answer. The correct answer is the first correlation is stronger. You say, wait a minute. Primary school math taught us that a negative value is almost always smaller than a positive value. Well, that's true, but also remember what we said, right? The sign in the case of correlation coefficient only denotes the direction of the correlations. So here it simply means that this correlation is negative association and this is positive correlation. That's it, right? Sign should not be considered when we evaluate the strength of a correlation. Let me repeat. Sign should not be considered when we assess the strength of a correlation. What we should pay attention to is the numerical value, right, without a sign, or the absolute value of the coefficient, right? So if we take the absolute value of the first correlation, it will be 0.8, right? And of course, the absolute value of 0.6 will be 0.6. And of course, 0.8, the absolute value of the first correlation is 0.8. The absolute value of the second correlation is 0.6. Well, 0.8 is larger than 0.6, therefore the first correlation is the stronger one. Okay? Alright, so don't consider the sign when you are determining the strength of correlation. Okay, so that's the meaning of, well, how we interpret, the sign and the value itself. And statisticians, have also worked out a certain criterion or several criteria to sort of a better stipulate, right, the strength of the correlation, because we know that if we only look at the numerical values, right, the smallest correlation will be 0. That means these two variables are not related to each other at all, or one, right, the two variables are perfectly related to each other, right? And of course the coefficient will take any value, right, in terms of the value itself without considering the sign, will take any value from this interval. Okay, so scientists or statisticians, they think, well, is there a way to sort of categorize the strength of the correlation depending on the specific intervals of the coefficients? So it's sort of a conventional agreement that if you find a correlation, the coefficient, right, it's smaller than 0.1 in terms of its absolute value, right, then we say that this correlation is barely there. Right? It's very, 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 very weak. Right? But if this coefficient is no smaller than 0.1, but no greater than 0.3, we'll say this is a weak correlation. And if the coefficient is greater than 0.3 and no greater than 0.5, we say this correlation is of moderate size or median, right? And of course, for any correlation that's greater than 0.5, we have a strong correlation. Okay. All right. So you should, for the examination, you should memorize this table. Okay, because I will have questions like this. I'll give you a correlation and ask you, well, is this, according to class, a weak, moderate, or strong correlation? Well, you should know if you memorize this table, right? This will be a weak correlation. What about this one? Negative 0.6. Wait a minute, there are no negative values here. But of course, we're talking about absolute values, right? So if you take the absolute value of this correlation, you'll be 0.6. 0.6 will be belonging to this category, so it's a strong correlation. Lastly, what about a correlation? 0.31, well, it's greater than 0.3, right? So it's going to be a medium correlation. Okay, easy. All right. Okay, so the next question, the next natural question will be, how do we come up with these numbers, right? Or these numbers. Okay. So now we're going to talk about how we calculate Pearson product moment correlations. Okay, this is the formula. Okay, so this is the coefficient, right? And x and y represents two variables, the x variable and a y variable. Okay, and then a equals to it's actually a ratio. Okay, well, I should say they're different formula to calculate correlations, but I chose one that sort of makes the most intuitive sense, I want to say. But we're not going to talk about the meaning of this formula. That's for a graduate class. But anyway, so this and this is actually easier to memorize. Anyway, so we have a ratio here, and the denominator is n minus 1, and the denominator is numerator is something that looks quite scary. But it's actually not scary at all, right? Because we just say x and y are two variables to be correlated. Want to know what's the correlation between these two variables, right? For example, x could be, in Andrew's case, right, political ideology, and y is the support for gun control. How much one supported, this issue. And zx and zy are the z-scores for each value of x and y. We know that from previous slides that Andrew surveyed 5 people, 1, 2, 3, 4, and 5, right? He scored 5 people, and each person provided two values, one for x, one for y, right? So this will be x1, y1, right? This will be the x for the second respondent, so you have x2, y2, x3, y3. You get the idea. Okay, so that means zx1, so each score will have a z value. Okay, so zx1, zy1, all the way to zx5 to zy5. Okay, so the z scores for each value of x and y. So that's that. Okay, and here we're taking the product of the z's. Okay, so there should be a multiplication sign, but we just know that this is multiplication, right? We multiply every z x and every zy, every pair of zx and zy, and we sum them up, right? To summation. We know from the formula of calculating means, and n is sample size. So these are all O friends. Okay, we just arrange them in a certain way, and then we have a new friend. And in the exam, hand calculation will be required, so I will provide this formula to you, and I will give you some fictional numbers, and you will calculate the correlations. Should be fun, always fun. So let's work together to understand how this formula really works. Okay, so this is the data. 5 individuals. We have 5 pairs of scores, right? So there's one pair of scores, second pair, all the way to the 5th pair. So the first question, of course, is what is the sample size? Well, that's pretty straightforward, I would say, because Andrew surveyed 5 people, so n is 5. Sample size 5. So second question is we're going to figure out all the x's. So what are the 5 values for x? Easy. 1, 2, 4, 2, 3. Okay? 1, 2, 4, 2, 3. And then from this constitutes a sample, right? And from the sample, we can calculate the sample mean and a sample standard deviation. And I sort of calculate this for you, but in exam, I might ask you to calculate these two by hand as well, because we'll talk about it, right? How to calculate mean and standard deviation. And what are the 5 values for y? Again, 2, 4, 5, 3, 2. 2, 4, 5, 3, 2. So again, right, you can easily calculate the mean and standard deviation for these 5 values. Boom, there we go. And then, given that this is the formula, the next step will surely be calculating z-values. Okay, so first step, right, after you have done all those, right, identifying the individual components, right? So step 1, find a z-score for all x values and y values. So, right, let's say here we have how do we calculate z-score for x1, right? We know that, the general formula for z is a certain value, let's say I'll use x, minus the sample mean divided by the sample standard deviation. Okay, so the z value for this guy will be 1 minus 2.4, right, divided by 1.14. What about z value for this second x, right? It would be 2 divided by minus 2.4 divided by 1.4. What about this, right? So it would be 4 minus 2.4 divided by 1.4. And you continue, right? Repeat the procedure to the remaining values, okay? And you do the same for y's, right? Using the mean and standard deviation for the 5 y's. So the y1 will be 2 minus 3.2 divided by 1.3, right? The y2 will be 4 minus 3.2 divided by 1.3, right? And then you repeat the procedure for the remaining y values. Okay, so easy, huh? Just very time consuming, but not difficult. All right, then you know, here I have calculated for you all the z values. So usually we have 2 decimal points, right? That would be good enough. And then the next step is we multiply each pair of zx and zy. So that means the first pair will be multiplying these two guys, right? Negative 1.23 times negative 0.92. Then we have the second pair, right? Negative 0.35 times 0.61. Third pair, 1.40 times 1.38. Fourth pair, negative 0.35 times negative 0.15. Last pair, 0.53 times negative 0.92. Okay, so we multiply each pair of zx and zy. So here we have 5 pairs of them. That means we should have 5 product terms. Okay, and what next? Well, next is we take the sum of these product terms, right? Sum the product terms. There we go. Add them all up. Okay. And last step is we divide the sum by n minus 1. Okay. Well, don't ask me why is n minus 1. It just is. Okay. And that should actually sort of remind you of the formula to calculate standard deviation. Standard deviation is what is the variance. Okay, well, the same, but I don't want a square root sign. So variance is what? The sum of the average distances of all values relative to the mean divided by n minus 1. Okay, so the same denominator here. Okay, it's a sort of adjustment because we're working with samples, not populations. But anyway, right, so here's the last step. Easy, huh? So we have here the first product term will be, well, this value here. I use 4 decimal points because that will give me more precision. It's sort of advisable that you do the same. Okay, and then I do the second multiplication. I have this value, and definitely pay attention to signs, right? Because that's very important. So 2 negative numbers, we have 1 positive number, so that's the product term. 1 positive, 1 negative, we have a negative number. Okay, so do pay attention to the sign, right? Don't forget the signs. And then repeat the procedure. Okay, boom, there we go. So we have all the 5 product terms, and then we sum them up. Okay, we sum all these up, and we have a, well, sum. Okay, and then we divided the sum with 4 because the sample size is 5. There we go. This value divided by 4, it will be 0.6, which is a strong correlation if we recall. Okay, so a simple way to check your answer is whether or not this value that obtained is bounded by -1 to +1. It could be a negative number. That's not scary, but it couldn't be -2, right? That would be wrong. It could be -0.9. That might be correct, right? But anyway, a value that's greater than 1 or smaller than -1 will be incorrect, right? Anything within this boundary might be correct. Okay, so that's sort of one way to check your answer. Okay, easy. Okay, so there will be homework assignment, the last homework assignment that will require you to calculate the Pearson product moment correlations. Okay, so that's it, and I will see you tomorrow.